I'm Ethan Fish. This is my CA6, the Compensator Design. First, we start with the problem statement, which is one basic problem in automated steering control is lane change maneuvers, where the steering input controls the lateral motion of the vehicle from one lane to the next. The automated steering controller is designed to steer the vehicle from the center of the current lane to the center of the adjacent lane. So for the objective here, we want to use the root locus method to design a compensator or controller to reduce the peak time to 75%. We want to maintain or decrease the overshoot of the uncompensated system in the compensated system and maintain a zero steady state error. We will also be plotting the root locus for the compensated and the uncompensated systems, along with the lane change step response for both the systems, and we will explain the reasoning. Okay, so here's the uncompensated system. From the block diagram below, we are able to find our transfer function here. We will multiply these crossed, then take that over 1 plus these multiplied by each other again, and our h of s, along with this 1 over s squared. And that's how we get our transfer function here. This is our completed transfer function solved out already. You see it's a fourth order system. Then we get into the step response of this uncompensated system. It has a gain of 2, damping ratio of 0.48, frequency of 0.09 radians per second. Then we get some MATLAB calculations to calculate the rise time, settling time, overshoot, the peak, and the peak time. The peak time is calculated from how long it takes to get to this maximum overshoot peak, if you will. So you see these numbers here, and those will get compared to our compensated system, kind of see how that changes and how the graph will look different. So here's a root locus of the uncompensated system. It's got 4 poles. You can see here is with the x's and 2 zeros, but they're both at -10 here, so it's kind of hard to tell, but there are 2 zeros there. Okay, and then for mine, for my controller, I chose a PID controller, which is a proportional integral derivative controller, or PID. This is an active controller. Quick background, there are 2 types of controllers, there's passive and an active. Big difference between the two is the controller PID is it responds to an error, and then it makes its modifications that way. A compensator will change the original dynamics of the plant, meaning that it won't respond to the error, it'll change the system itself to correspond with that error. Okay, we'll talk a little about the PID and kind of what happens with it. So a 0 is placed close to its pole located at the origin. And we can use MATLAB to find this 0 where it would be located. Also use MATLAB to find the appropriate K value for this system. The lowest part of the system dominates the response, so we can ignore the faster parts. So we took that fourth order system and we can simplify it down to a second order approximation. In the PID controller, it uses 3 variables, Kp, Kd, and Ki. Kp is a proportional gain. It affects by proportionally increasing the control signal for the same level of error. This tends to reduce steady state error. Kd is a derivative term, adds ability of the controller to anticipate an error that's coming. Ki is the integral term, helps reduce steady state error. Here we have the transfer function for a PID controller, seen here. And we have pretty much the same transfer function or block diagram as the uncompensated system, but we added that PID here. Then we were given these variables here for the open loop transfer functions here. We take those variables and we find the complete transfer function of closed loop transfer function here. Now we go to the step response of the compensated, and this is also compared to the uncompensated. Kind of see the difference in what changed and what didn't. So the pros are reduce the peak time and a quicker rise time. The cons are it's a larger range of settling time. Which you can see here is that little oscillation that happens here. It's not a gentle, goes back to the center. It has a larger overshoot, and that takes a longer time to settle. But that reduced peak time, as you can see, this rise time, how fast it goes from this angle here, the slope here, and then the peak time is that maximum peak here, how long it takes to get to that peak. So you can see here it goes down to 4, and then for the uncompensated, it'll be around 7, or it was around 7. So the peak time for the compensated one was 4.7794 compared to the 7.1987 that we had in the uncompensated one. You can see some comparisons here, the rise time, settling time, overshoot, and the peaks. Like I said, the peak was a little higher in this compensated one, but the peak time was substantially smaller, which was the goal of this controller here. And now we have the root locus of the PID controller, which it looks almost the same, but then you see this extra pole and 0 here by the origin, which is related here. We have 5 poles, 3 zeros compared to the 4 and 2. We have these 2, then this other 2, and then the third one, or the 5th one here. And this had a frequency of 1.22 radians per second. This is my controller design. Thank you for listening.